Assalamu alaikum everyone. Myself H. Muhammad Ibrahim, currently pursuing BE Electronics and Communication Engineering. As part of my internship at MFC Information Technologies, I worked on developing an EV ADAS dashboard using the STM32 Blue Pill microcontroller along with a Python based dashboard. Today in this presentation, I would like to take you through the complete journey of this project and then what the project aimed to achieve, how I built it, the tools I explored in this project, the challenges I faced, what I learned during the internship, and finally, I will give you a live demonstration of the system. Before we begin, here is a quick review of today's presentation. First, I will explain the goal of this internship project, then I will walk you through the system architecture and my development journey, and then after that, I will discuss the tools I used, the major challenges I faced and how I handled them, the key learnings from this internship, and finally I will demonstrate the EV ADAS dashboard in action. Before getting into the implementation, it's important to understand what this project was actually meant to achieve. The main objective was to move beyond basic embedded programming and build something that resembles a real automotive embedded application. Through this project, I got the opportunity to learn embedded C in a practical environment and then understand how ADAS safety logic works, build a system with real-time vehicle behavior, and work with continuously changing data instead of simple serial outputs. So this project was not just about writing code, it was about understanding how different embedded modules work together to create a complete system. Now let's look at how this project relates to a real automotive system. Even though everything here is simulated, I want the overall design to resemble a real embedded EV's architecture. On the left side of the slide, we can see a simplified EV powertrain consisting of the battery pack, inverter, and then the motor wheels. In my project, these are represented through the EV dynamics model where vehicle speed, motor torque, and then the battery state of charge, regenerative braking, and remaining driving range are calculated continuously. On the right side, we can see three sensor ADAS layout similar to what's commonly used for front obstacle detection and then blind spot monitoring. And the project is also designed around the same concept using three ultrasonic sensors. And the idea was not just to build a simulation but to understand how these concepts are applied in real automotive embedded systems. Okay, now let's see how the complete system actually works. The accelerator, brake, and ultrasonic sensor inputs are first read by the STM32 Blue Pill, and then in the next state, inside the firmware, the application is divided into separate modules responsible for EV control and then ADAS decision making and fault monitoring. After processing all the inputs, the STM32 sends the vehicle information to the Python dashboard through UART communication at a baud rate of 115200, and then the dashboard then displays vehicle speed, battery status, motor torque, and then remaining indicators in real time. This modular architecture made the project much easier to understand, debug, and expand. Okay, I did not build this project all at once, but I developed it in three major stages. The first stage was building the firmware foundation, which includes the GPIO configuration and then ADC interfacing, timers, and the EV dynamics module, etc. Once that was working, I moved on to implementing the ADAS logic and then the fault handling and UART communication between STM32 and the dashboard. Finally, I focused on visualization and testing by developing the Python dashboard and adding the features required to monitor and demonstrate the complete system. Building the project in stages helped me debug each module individually before integrating everything together. Then the slide tools I explored along the way is throughout this internship I got the opportunity to work with several tools commonly used in embedded system developments. First I used STM32 Cube IDE for firmware development using embedded C and HAL drivers. And then the PICSimLab was used to simulate the STM32 Blue Pill without requiring any physical hardware. And Python and Matplotlib were used to build the dashboard and visualize the vehicle data in real time. I also used the Terraterm for UART testing and COM0COM to create virtual serial communication between the simulator and the dashboard. Working with all these tools together gave me a much better understanding of the complete embedded development workflow. And then here are the challenges, limitations, and where I am today. This project is this project also taught me that embedded systems are not just about coding, they are equally about debugging and solving problems. One issue I faced was that STM32 Cube MX regeneration sometimes overwrote custom code placed outside the protected user code sections. After understanding how CubeMX generates projects, I was able to organize my code properly. And then the another issue was a blocking delay inside the ultrasonic sensor routine, which affected the execution of the main loop. And then after debugging the firmware step by step, I identified the cause and resolved it. However, the biggest challenge I faced was with the ultrasonic sensors in the PICSimLab. My original plan was to demonstrate the complete ADAS functionality using live ultrasonic sensor readings from the simulation, but I successfully completed the firmware, EV control logic, UART communication, and the Python dashboard while interfacing the HCESR04 sensors inside the PICSimLab simulation environment. I started getting inconsistent sensor behavior, and then due to the limited internship timeline, I could not completely debug this issue before the project submission. Okay, so instead of leaving the ADAS functionality incomplete, I thought about how I could still demonstrate the complete system in a meaningful way. That's when I implemented the run obstacle detection test feature in the Python dashboard. What this button does, when this button is pressed, it executes a predefined obstacle scenario that simulates a vehicle approaching an obstacle. It just simulates, not the real data. This allows the complete ADAS workflow, including collision warning, and then the critical alert generation, emergency braking, and then vehicle recovery to be demonstrated consistently. The important point is that the firmware architecture, the EV control logic, UART communication, ADAS decision making remain exactly the same. Nothing is changed. Only the obstacle input is simulated so that the complete ADAS behavior can be demonstrated reliably within the available internship timeline. Looking back, I feel this experience taught me an important engineering lesson. Not every problem can be completely solved within the deadline, but it's equally important to identify the limitation, be transparent about it, and find a practical solutions. Overall, this internship was a valuable learning experience for me. Technically, I gained hands-on experience with STM32 programming, which I was not aware of, embedded C, Hall drivers, ATC interfacing, UART communication, and then the timers, modular firmware development, and the Python dashboard integration was also interesting. More importantly, I learned how different embedded modules work together to build a complete embedded application instead of working as isolated pieces separately. I also became much more systematic in debugging by breaking problems into smaller parts and solving them one step at a time. This project has given me much more confidence to work on larger embedded systems in the future. And then that brings me to the end of my presentation. Now let me demonstrate the EV ADAS dashboard and show how the complete system responds during the obstacle detection test. Okay, now that I have explained the project, let me demonstrate how it has been actually implemented. I will begin with the firmware developed in STM32 Cube IDE. This is the complete STM32 project used for the EV ADAS dashboard. First of all, the pinout and configuration. This is the pinout and configuration generated using STM32CubeMX. Here we can see that the peripherals required for the project, the ADC channels are used to read the accelerator and brake outputs, and then the UART is configured for communication between STM32 and Python dashboard. And then the GPIO pins are configured for ultrasonic sensors, and then the buzzer, LEDs, and other required peripherals. And then using STM32 made the peripheral configuration much easier and allowed me to focus more on the application logic. This is the main thing. Now let's look at the project structure. Instead of writing the complete application inside a single file, this project followed a modular programming approach. Each module has its own responsibility. For example, the ADAS, command.h file, demo, EV control, fault, main, the UART shell, ultrasonic. Each file has its own responsibility in this project. Now next, this is here on the left side. This is PICSimLab, which is simulating the STM32 Blue Pill microcontroller. Here we can simulate the accelerator input, brake input, and then the ultrasonic sensors without requiring actual hardware. The firmware running inside this simulator is exactly the same firmware that I showed in this STM32 CubeID. As the firmware executes, all the calculated vehicle parameters are transmitted through UART to the Python dashboard. Now let's move on to the dashboard. Okay, let's open the Python dashboard using the command prompt. Here we will type the location of the file where we have saved the Python file. We'll open the file. Also we will enter the port number at which we are connecting the PICSimLab and the Python dashboard. Enter. I think there is an issue. Let's find what's the issue. Should open now. Dash. I think it's loading. Yeah, here is our dashboard. Initially, we can see that instead of displaying raw serial data in a terminal, the dashboard provides a much more user-friendly interface. Here we can monitor the vehicle speed, and then battery state of charge, remaining driving range like motor torque, accelerator, brake, motor temperature, fault, etc. And then here is the live graph. So we will first accelerate the vehicle by increasing the acceleration pedal in the PICSIM simulator. Here we can see that the speed is gradually increasing, and also the battery and the range is decreasing, and here we can see the torque is also increased. All these values are updated in real time using the telemetry received from the STM32 firmware. And the dashboard is simply displaying the information received through UART. Now I will slowly release the accelerator. Let's slowly release the accelerator and increase the brake pedal to 100%. Okay, here we can see that the brake is at 100% and the speed is now gradually decreasing. We'll also here notice that the motor torque also becomes negative. This represents regenerative braking, where the motor acts as a generator while slowing down the vehicle. Once the vehicle stops, the dashboard returns to its normal idle condition. Okay, now I would like to demonstrate the most important feature of this project, the run obstacle detection test. Before starting the demonstration, I would like to briefly explain why I added this feature. My original goal was to demonstrate the complete ADAS system using live ultrasonic sensor readings from the PICSimLab, but unfortunately, However, while interfacing the ultrasonic sensors inside the simulation environment, I encountered inconsistent sensor behavior. Because of the limited internship timeline, I could not complete debug that issue before the project submission. Instead of leaving the ADAS functionality incomplete, I decided to run the obstacle detection test feature. Okay, now we will run this feature. Run obstacle detection test. Okay, it is running. Now the obstacle distance decreases and the dashboard generates a warning alert. This indicates that the vehicle has detected a possible collision between the two vehicles. The test has started. Now the vehicle will come close. We will release the brake and give some acceleration so that the vehicle continues moving. Should not take so much time. I don't know why it's taking so much time. Yeah. Now the distance between the two vehicles is decreasing gradually. As the obstacle comes even closer, the system enters the critical state. At this point, the emergency braking logic activates automatically. The vehicle drops speed rapidly, and the emergency brake status becomes active, and the alarm indicators changes accordingly. Finally, as the obstacle will move away from the vehicle, the warning clears automatically. The emergency braking is also released. It will happen now. Okay, this demonstrates the complete ADAS workflow from obstacle detection to collision warning, emergency braking, and then system recovery. So this completes the demonstration of my EV ADAS project. Although this project was developed in a simulated environment, it provided me with practical experience in STM32 firmware development. Thank you once again. I hope this presentation and demonstration gave you a clear understanding of both the project and my learning journey throughout the internship. Thank you.